This time I'm going to speak about electron transfer, but before that I need to mention what's a wavelength and a frequency. When you speak about one wave, you need to say something about the wavelength, frequency of that wave, and also amplitude of that wave. The way we show them, we say the distance between two identical points. For example, two maximum points, the distance between them, so that one is going to be wavelength, and we show it by lambda. And if you choose one point and you try to count number of cycles that's passing that point in 1 second, then you're dealing with a frequency. Frequency, in other words, is number of cycles that's passing this specific point in 1 second. So we start from here, that's the starting point, and one cycle in 1 second, one cycle is passing, so one cycle in 1 second. So we say the frequency is going to be 1 cycle per second, and it has unit of 1/second or hertz. And wavelength, it has unit of meter. And the last thing we need to cover is the amplitude. Amplitude is the distance between the horizontal line and the maximum point or the minimum point. That one is going to be the amplitude. We show it by A. Amplitude, it will tell you intensity of the light or the wave. So amplitude, it will show you intensity of that light. Well, wavelength and frequency, that we show it by nu, they will tell you energy of any wave. Now I'm going to bring two examples that they are dealing with electron transfer. I need to calculate energy of each electron transfer, and because I know energy is connected to wavelength and frequency, so I can calculate wavelength and frequency of that energy, that electron transfer. I go with first case, that is electron transfer from lower level to higher level. So case 1, we have electron that's sitting inside n equal 3, and we're sending electron to n equal 7. So thing we are dealing with it, we have one electron that is sitting inside lower level of energy, and we are sending this electron to higher level of energy. In order to send electron to higher level, we need to apply energy. So I'm going to apply energy to send that electron to higher level. And energy that's I'm applying is going to be equal to h nu. The only thing I know about this energy is that this energy is equal to h nu. Now I want to calculate how much change happened with the energy during electron transfer from n N3 to N7. And thing I need to mention here, because we are sending electron from N3 to N7, from lower level to higher level, is electron transfer is going to be absorption. So with absorption, always final N is bigger than initial N. So our electron at the beginning had energy equal to EI. We gave it H nu energy, and nu energy now is equal to E final. If I subtract EI from both sides, I will get H nu equal to EF minus EI, or final energy minus initial energy. And you know that E final minus initial energy, we can name it delta E, change with energy. So H nu will be equal to delta E. Well, we know electron transfer, change with energy during electron transfer, can be calculated through this formula. Delta E equal to minus Rydberg constant equal to 1 over square of final N minus 1 over square of initial N. So if I can calculate delta E, another word, I got H nu. H is constant, so now you can calculate nu, which is the frequency. So we got delta E equal plus H nu, and from other side we got delta E equal minus Rydberg constant to 1 over square of final N minus 1 over square of initial N. Left side are delta E for both formulas, so I can say H nu is equal to minus Rydberg constant to 1 over square of final N minus 1 over square of initial N. RH is equal to 2.18 multiplied 10 minus 18 joule. We are sending electron from N equal 3 to N equal 7. So initial N is 3 and final N is 7. So H nu will be minus 2.18 multiplied 10 minus 18 joule multiply 1 over final N is 7. It will be square of 7 minus 1 over initial N is 3, so it will be square of 3. So H nu will be minus 2.18 multiplied 10 minus 18 joule multiply 1 over 49 minus 1 over 9. Hold this part. It has negative answer. So negative multiply negative is going to be positive, and h nu will be equal to positive number. And it has to be positive because h is constant number and the frequency always has to be positive number. We cannot have negative frequency number. So h nu will be equal to plus 1.977 multiply 10 minus 19, and unit for it is joule. Okay, so I got h nu equal to this number. Now I need to find the frequency. H, or Planck constant, is equal to 6.626 multiply 10 minus to power minus 34 unit joule to second. So frequency will be equal to whatever we got until now, which is energy, or delta E. It will be divided by h. So 1.977 multiply 10 power of minus 19 unit joule, and you divide it by h. So 1.977 multiply 10 power of minus 19 unit joule divided by h, which is 6.626 multiply 10 power of minus 34 unit joule to second. You cancel joule by joule and you will get unit of 1 over second. The answer is 2.984 multiply 10 the power of 14 unit 1 over second, or hertz. Last step that we want to do is wavelength of this electron transfer. You got the frequency, so calculation now is easier. C, or velocity of light, it's equal to wavelength multiply frequency. So you will be given number of C, and you got the frequency, so you can calculate wavelength. As I said, they will give you C, and C is equal to 3.00 multiply 10 plus 8 meter over second. This is exact number, so you don't need to worry about the sig fig here. And the formula is C is equal to wavelength multiply frequency. We got frequency equal to 2.984 multiply 10 to the power of 14 unit of 1 over second, or hertz. So wavelength will be C over frequency. So wavelength will be 3.00 multiply 10 power of 8 meter over second divided by frequency, which is 2.984 multiply 10 to the power of 14 1 over second, or hertz. Now you can cancel second by second and you will get meter as a unit for wavelength, which is the right unit for wavelength. And the answer for it is 1.005 multiply 10 to the power of minus 6 meter. If they are asking find wavelength in nanometer, you can do this conversion factor. You can do this conversion. That is 1 nanometer is equal to 1 multiply 10 to the power of minus 9 meter. So you can say 1.005 multiply 10 minus 6 meter multiply 1 multiply 10 to power of minus 9 meter equal 1 nanometer. So the answer will be 1.005 multiply 10 to the power of 3 nanometer. So first case that we just actually solved a question for it was electron transfer from lower level to higher level. Next one, I will do one math calculation. That's we are dealing with electron transfer from higher level to lower level. So, second case, we are dealing with electron transfer when electron is sitting in higher level, like n equal 5, and we are letting electron to go to lower level, like n equal 4. I should say one thing. If electron is sitting inside n equal 5, that means it has higher energy than any electron that's sitting inside n equal 4, or anyone that is sitting inside n equal 3. So energy of n5 is higher than energy of n4 and higher than energy of n3. So I can say here energy for one electron that's sitting inside n equal 5 is bigger than energy of one electron when n is equal 4, and is bigger than energy of one electron that's sitting inside n equal 3. So if this one is correct, when you're dealing with one electron transfer that's dealing with transferring one electron from n equal 5 to n equal 4, because energy of n5 is bigger than energy of n4, that electron during relaxation or electron transfer will release some of the extra energy as a light. So we will have some emission, and that emission, it has energy of h nu. So if I want to write one formula for one phrase for energy of this electron when it's sitting inside n equal 5, I can say energy of that electron at the beginning was equal to EI. During electron transfer, lost energy equals to h nu, and its final energy now is equal to EF. If you subtract EI from both sides, like the previous case we did, we will get minus h nu equal to EF minus EI. And we know right side we can write it as a delta E. So when you're dealing with electron transfer, that is emission, or from higher level to lower level, delta E, or change with the energy, is equal to minus h nu, not plus h nu. So initial n was 5, so Ni is 5. We send the electron to lower level, or final n is going to be 4, and you have RH equal to 2.18 multiplied 10 to the power of minus 18 joule. H, or Planck constant, equals 6.626 multiplied 10 to the power of minus 34 joule to second. C, or velocity of light, is equal to 3.00 multiplied 10 to the power of 8 meter over second. Now you can use all these constant numbers and calculate frequency and wavelength of this electron transfer. I go with this fact that delta E for this electron transfer is equal to minus h nu. And I know delta E I can calculate it through this formula. Minus Rydberg constant equal to 1 over square of final n minus 1 over square of initial n. Replace delta E by minus h nu, so you get minus h nu equal Rydberg constant is 2.18 multiplied 10 to the power of minus 18 unit joule, multiply 1 over final n 4, so it will be square of 4, minus initial n is 5, so it will be square of 5. So minus h nu equal to minus 2.18 multiplied 10 to the power of minus 18 joule, and this one will be 1 over 16 minus 1 over 25. Answer for this part this time is a positive number. Positive multiply negative number is a negative, but you have a negative on the left side, so they will cancel each other. We got h minus h nu is equal to minus 4.905 multiply 10 to the power of minus 20 joule. Minus to minus will be positive, so h nu is equal to positive number. Now, said h nu equal to plus h nu is equal to 4.905 multiplied 10 to the power of minus 20 joule. So frequency will be delta E, or energy, change with the energy until now, divided by h, and replace h by Planck constant number, which is 6.626 multiplied 10 power of minus 34 joule to second. Cancel joule by joule, you get frequency equal to 7.403 multiply 10 to the power of 13, 1 over second, or hertz. So we got the frequency. Wavelength, you can find it through C equal lambda, or wavelength multiply frequency, and wavelength lambda is equal to C over frequency. C is equal to 3.00 multiplied 10 to the power of 8 meter over second, divided by wavelength frequency, which is 7.403 multiplied 10 to the power of 13, 1 over second. Cancel second by second, and you get meter. And answer for lambda is equal to 4.052 multiplied 10 to the power of minus 6 meter. So we practice two cases. One, electron transfer from lower level to higher level, or absorption, and the second one from higher level to lower level, or emission. So if we are dealing with electron transfer from lower level to higher level, or another way, if n final bigger than n initial, in that case you are dealing with absorption. And the correct formula to write is initial energy plus h nu is equal to final energy, or EF minus EI equal to h nu. So delta E is equal to h nu. But if you are dealing with a case that's final n is lower than initial n, then case you are dealing with is emission. With emission, you need to write this one, EI minus h nu. That electron will lose some energy to get final energy of EF. So EF minus EI equal to minus h nu. So delta E equal to minus h nu. Compare these two. When you are dealing with absorption, delta E is equal h nu. When is emission, delta E is equal minus h nu. And in both cases, you know that delta E is equal minus RH 1 over square of initial final n minus 1 over square of initial n.